In this video, we're going to build a multi-layer perceptron using TensorFlow and implement it as a classification model through coding. The coding file is available on GitHub for you to download and run. First, let's take a look at the dataset we'll be using for our classification model. In this coding example, we're using the wine dataset, which is one of the most widely used example datasets in AI classification models. As you can see on the slide here, it includes 13 features, such as alcohol content, malic acid, and ash content. The labels are divided into 3 categories, labeled as 0, 1, and 2. There are a total of 178 data samples in the dataset. So basically, this dataset is used to classify wine into 3 different types based on 13 features. First, let's import the libraries we need for coding. We'll use pandas for handling Excel-like data, NumPy for numerical calculations, and scikit-learn for data pre-processing and splitting the dataset into training and testing sets. For data visualization, we'll bring in matplotlib. And finally, we'll import TensorFlow to build our deep learning model. First, we load the wine Excel file and store it in the variable df. Then, we separate the data. The first 13 columns, excluding the last one, are stored in XOR data, and the last column, which indicates the type of wine, is stored in Y data. Next, we convert both X data and Y data into float type to prepare them for training the neural network model. Using the dot shape command, we can check the structure of the entire wine dataset. There are 178 rows and 14 columns in total, and we can also see the shape of both the X data and Y data this way. Then, we use the train test split function to split the dataset into training and testing sets in an 80-20 ratio. After that, we use the min-max scaler to normalize the X data so that all the values fall between 0 and 1. Since there are 178 total samples, 80% of them, so 142, are used for training and the remaining 36 samples are used for testing. In the previous video, we looked at how to build an artificial neural network using TensorFlow. This time, we'll use the add function from the sequential API to build our model. The diagram you see on the screen shows the structure of the neural network we're going to create. It's made up of an input layer, a hidden layer, and an output layer. Looking at the wine dataset we're using, there are 13 input features in the X data, and 3 classes for the wine types. So, the input layer will receive 13 values, and the output layer will produce 3 outputs, which will be passed through a softmax function to give us probabilities for each class. As for the hidden layer, there's no fixed rule for how many nodes it should have, but in this case, we'll go with 32 nodes. First, we start by defining the model with sequential, and then we use the add function to add each layer one by one. We create an input layer named input, a hidden layer named hidden one, and an output layer named output. Here, the number 13 represents the number of input features. 32 is the number of nodes in the hidden layer, and 3 corresponds to the number of wine classes. For multi-class classification, we use the softmax activation function in the final output layer. Now it's time to compile the neural network model we've built. We'll use the Atom Optimizer as our optimization algorithm, and we'll set the learning rate to 0.01. For the loss function, since our class labels are integers, like 0, 1, and 2, we'll use sparse categorical cross-entropy, which is designed for this type of label format. And for evaluating the model's performance, we'll use accuracy as our metric. Just as a side note, If your class labels were one-hot encoded instead of integers, then you'd use categorical cross-entropy as the loss function instead. Next, we train the model using the training data xtrain and ytrain. We'll set the number of epochs to 300 and the batch size to 16. The loss and accuracy values that come out during training will be stored in a variable called history. As the model trains over 300 epochs, you'll notice that the loss gradually decreases and the accuracy improves, reaching around 0.95 by the end of training. After the training is complete, we evaluate the model's performance using the test data. By using the evaluate function, we can get the loss and accuracy. The accuracy we get is 0.9722, which means the model achieved 97.22% accuracy. Additionally, using the matplotlib library, we can visualize the changes in loss and accuracy over the course of training in a graph. As you can see here, the history variable stores the model's loss and accuracy values. By plotting these values, we can see that the loss decreases and gets close to 0, while the accuracy increases above 0.9 during the training process.